I get my timer on? So, before the break, we basically did this problem, and it's a very standard problem. We basically recognize that we're in equilibrium, so the sum of the forces equals 0 in any direction. And because it's a two-dimensional problem, it made sense to do a horizontal summation and a vertical summation. And so I have to be careful to use components. I can't just use the original forces. I've got to use components. And so once I've set up the two basic equations, I'm doing math. And I'm basically saying, well, a cosine is just a fraction between 0 and 1. So it's just I've got a fractional number times TR and a fractional number times TL equals 0 in the green. And I have a fractional number times TL and a fractional number times TR plus minus 30 equals 0 in the red. And the rest is math. You've got to do the math right, but the physics bit is done at that point. And so it's long, and I'm not writing all those things down so that you learn. I'm writing all those things down because I want to get the right answer. Because I don't learn these answers. I just do physics. And if I jump steps, I will make slips. And so I write all that down because I need it. I want a write-up where I can look at every line and see it logically comes from what comes in front. Because that's how you catch mistakes. If you do a step or two in your head, then you can't check it very easily. And that's where I see people making mistakes. And it's not that as your tester, I can just turn around and say, oh, they know how to do this. I've got to turn around and say, no, this is the wrong number. And that has consequences for it. You've got to get the right numbers. So slow down. And I'm not being mean. On some people's tests, I wrote down, just a couple of people, I wrote down, you had 60 minutes to find this slip. And I'm not being mean, kind of going, how dare you leave early. It's that, think about it. You had 60 minutes to find this slip. And you thought you were done and you went. And, if you'd done 5 minutes, you'd have got, an extra point or two. And that counts. So just slow down. By and large, most people have time. It's like, it's just that they are used to kind of boom and doing stuff in their head, and they pay a price for it. It's a shame to pay a price and lose a letter grade over a semester because it's just a habit of doing things in your head. However, I like to be efficient, so I'd like to find a more efficient way of doing it, and actually I have one. Now, the inefficient bit is I have to actually erase all this. So let me see if I can do that. So come down here and I'll find the biggest eraser I can find. Oh, was that erase all ink? Erase all ink on slide? These guys are just amazingly good. Okay. So now, let's get my pointer back. And let's do the pen, and I'll do the color. So I have my two axes. Oops. So I have my two axes. And then what I want to do is I'm going to have this guy over here, and that's going to be at 30 T right, and that's 30 degrees. I've got to be really careful with this diagram. This is the disadvantage of this method is if my diagram is sloppy, I will get confused. So I want to make sure that that is higher. Okay, but not too high. That looks kind of okay, and that's T left. If I was doing this on paper, I'd probably get a nice little protractor and do it right, and then have this guy down here. So there's my setup, and now I'm going to go, and what I'm going to do is I'm going to say, what do I want to find? What do I want to find? T left. And I'm going to turn around and say, the problem with the method I just showed you is that when I do an X component, when I say the sum of the forces horizontally equals 0, both T left and T right are included. When I do the vertical sum of the forces equals 0, both T left and T right are included. If I could find a direction, an axis, where only T left had a component, then I would be just made. I could do it in one line. So you've got to focus on T right. I'm trying to find T left, so focus on T right and say, what axis does this force have no component in. And it's going to be what's orthogonal to it. So I'm going to go, let's get a different colored pen. Let's go to, because this is like, so it's beautiful. This is like happiness. What you do is you go to this guy and you say, I'm going to draw a line that's at 90 degrees to it. I don't want TR. I want to find TL. So I want a line that's at 90 degrees to the thing I don't want. Agreed? And then, let's get a different colored pen so you can see it. Let's go to purple. So then I look at this and I go dot, dot, dot. There's the component of TL along the green line. And I've got to do some geometry here. If this is 30, what angle is this? 30, 60, because that's a right angle. And then this is a right angle, so 60, 30. If this is 30 and that's 40, what angle is this in between? 20. That's the one I want. So this would be TL cosine 20. Can you see it? You basically picked the green line because it was perpendicular to T right, and then you propagated your angles, so you said 30 plus 60 makes a right angle, and then because T right is perpendicular to the green line, we said 60 plus 30 equals 90, so that's 30, and then I looked at this quadrant, the top left-hand quadrant. I know there's a 30 there, I know there's a 40 there, that leaves 20 in the middle. So I know the angle between my original vector and my component is 20 degrees.
What told you that the green line is perpendicular to TR?
I chose it. I designed it because that's the only axis for which TR has no component. Think of a component like a shadow. If a vector's like that, it kind of casts a shadow down here. And if it's like that, it kind of casts a longer shadow. That's a bigger component. Same vector, a smaller component. Same vector, a smaller component. Same vector, no component. So by going at 90 degrees to an axis, I have no effect on the axis. So it's really nice. On this side, let's go down here. So we go dot, 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 dot. And then I go, there's my component for this guy. I got to do some more geometry. Well, let's look. That green line is a straight line, and that vertical is a straight line. If that's 30 degrees, what's this angle down here? 30. Can you see it? So that means that this guy is going to be 30 cosine 30. Now, there's a bit of a problem. These guys are fighting each other, agreed? Yeah, the two vectors, the two purple vectors are fighting each other. But I got them both down as positives at the minute, so I have to pick a sign, a direction sign. So I'm going to say up and to the left is positive and down and to the right is negative, and it doesn't matter as long as once you've picked it, you stick with it. So I'm going to say, oh, in that case then, that's a positive and that's a negative. Now watch this. The sum of the forces along the green line equals 0. Positive TL cosine 20 added to negative 30 cosine 30 equals 0. TL is equal to 30 cosine 30 over cosine 20, which equals, you get your little calculator, you check your own degrees, and you're going to say cosine 30, enter, divided by cosine 20, enter, times 30 for the length is equal to 27.65 newtons. Isn't that what we got last time? And isn't this a lot quicker and a lot simpler? Now, you've got to know your geometry. So it's like, yeah, you want to play baseball, you've got to learn to catch. You can't just be a good hitter, and you can't just be practicing your swing all the time. You've got to learn to catch as well. So you've got to learn to catch on this. Yeah?
Why is the all the forces on the green line equal to 0?
Is the traffic light accelerating anywhere? So that means in any direction, the sum of the forces equals 0. And I just happen to pick a convenient direction. Now, there'll be times when that's not true, and I've got to be a bit more careful. But when the object is truly not accelerating in any direction, I can pick any axis I want. Cool? So I understand if you like the first method because, you know, it's like the geometry is not there. But I want to encourage you, as you feel comfortable, to practice your geometry and move across to the second direction. Because as we go through this course, we're not going to be able to do the verticals and the horizontals all the time and finish. We're going to have so much work to do. It's going to get so long. So there is a penalty for not learning what axis to use. And later on, there'll be a penalty for not learning what axis to use when you're doing talks. The problems will get long. Yes?
Excuse me. When you had both, you said, I didn't understand when you said you have to choose which one. When you decided which one's positive, which one's negative?
Oh, so it does not matter. This is it positive because it's upwards? Well, yeah, but it's also to the left, so you could argue it should be negative. And so it's arbitrary choice, but you must pick. Okay. One of them must have a positive sign and one of them must have a negative sign. And from then on, for this problem, you have to live with that choice. But you can choose, and you often...
Same result.
Yeah. You'll pick, and as long as you stick with it, you'll be fine. Cool? Everybody okay? Yes?
On the left, because you made the green line perpendicular to TR.
Yep.
And then the value for TL, you say TL cosine 20. Does it matter, because it's on the left, the cosine 20 shouldn't be like negative because the angle it's...
Cosine of 20 is a positive number.
Yeah.
Doesn't matter which orientation it's at, it's a positive number. Now, some people prefer to use the big angle.
Yeah, because you're turning the whole thing.
Yeah, and then there's like issues because what did you decide to call this guy? So my advice, I'd never use an angle bigger than 90 degrees. I never use them. I just look at my diagram and get my signs from there, and then I do my angles that are less than 90. So watch out for that.
I have a question.
Yep.
What made you put the green line parallel to TR, although we're looking for TL?
I didn't make it parallel, I made it perpendicular.
Perpendicular.
Because I don't want TR in my equation. So if TR is here, by having the axis perpendicular to TR, it casts no shadow, which means it has no component. That TR causes it's got no influence to the left, it's got no influence to the right along that line. But if I had TR and I had picked a line like that, it would have cast a shadow, and I would have had to include it in my equation. Remember, the sum of the forces equals 0 along a direction. And so the trick with this is I picked a direction deliberately which was 90 degrees to the force I wanted to be able to ignore. So you say, what do I want? What do I want to get rid of? Let's go at 90 degrees to that. Cool. You got a question or a comment?
If we were to specify TR, would we make the green line perpendicular to TL?
Exactly. Yeah, that's exactly. Good. Very good. So please embrace this. It makes life a lot easier. I want to do another thing, which is the other example. I'm going to do one of each, and then next time, if we get time today, we'll start it. But I don't think we'll get time today. we'll actually practice these. The next chapter it's not the next chapter in the notes, it's the next chapter in our presentation is more complicated examples of these two things. So I want to give you a taste of both of them. This next thing is so-called dynamics. And so a classic example is a mass on a frictionless table with a piece of string going over a frictionless, massless pulley and hanging from a mass from that. So, and it's an idealized case. There's another one which we do in lab, which is so-called Atwood's machine, where we simply have the mass on one side of a pulley and we have a different mass on the other side of the pulley, big M and little m. And we say, how does this system behave once you release it? So there's a whole family. We could have a mass on a slope, and I could have massless, and I can even have I can even have friction. So there's various combinations I can do in this. We're going to start off with a relatively simple one. It's a frictionless table, and it is two masses. So, yeah, frictionless. There's no friction there. So we're going to say, let's write that down, frictionless. Frictionless interface there. Good. Okay. So this is layout becomes important, and the problem is with signs. So, can you tell me, let me ask you, is this, so first of all, I don't have time, okay. We'll do it real quick, because I am curious. Question, give me A if you think this will not move, give me B if you think that this will, so A is not move, B is coast, that means constant velocity, and C is accelerate. When you let this thing go. So you're just going to let this thing go. You take your finger off it, and you're going to say what happens next. So give me A, B, or C. Gravity's going downwards.
Do we happen to know four's mass?
Do we happen to know what?
The mass of number 4?
That is the mass.
Yeah.
It's not newtons.
It's mass. When it's inside the box, I mean it as mass.
4 kilograms.
So that's a 7 kilogram block on the table and a 4 kilogram load handed in space. Got 18. You can change your vote. If you decide you want to change, you can change your vote. Let's have a look. I'll give you just a few more seconds. I'll go up to 15 on the... if I can find my thing to stop it. Didn't mean to do that. Didn't mean to do that.
Say cancel.
There is no cancel.
The X.
The X close.
Oh, is that right?
Try keep them.
I don't want keep.
Okay, disregard it.
Okay, stop.
Oh, discard.
And we'll look. Oh! So, this thing is going to accelerate. It's not, it is going to move, because it's a frictionless table. It is going to move. And not only is it going to move, it's going to accelerate. So, this might not work out so well. So, let's have a look. Let's get rid of you.
Discard.
And then keep. I'm going to try keeping. I'm going to go to from the beginning. Oh, this is like. Oh, this is one. Oh. Okay. So so C is the right answer. Oh. So let's have a look. I think it's because I've got the pen. So let's go into here. Printer options. Go to pen. Go to here. Go to printer options. Go to. Why can I not have a eraser? Oh, because why can I not have an eraser? Anyway, it doesn't matter. I'll work around it. Okay? So basically, what do we say? Trick number 1. You've got to draw this thing out. You've got to take this force down here, which will be 40 newtons, and you've got to turn it around so that it's 40 newtons in that direction. You've got to get rid of this corner, because this corner is going to kill you. And we have tension. What's pulling this 7 kilogram mass forward is the tension in the string, and what's pulling that 4 kilogram mass backwards is the tension in the string.
But I thought the gravity's acting on the floor.
Yep, it is. There's gravity pulling it.
So 40 times the gravity is going to be a lot more than the 7 or 70. So it has to accelerate.
That's where we're going to, yeah. So what we do is we say, okay, what do you want to find out, Bonaquisti? And there's 2 things I can find out. One is I can find out the acceleration, and the other thing I can find out is the tension. The harder thing is to find the tension, so that's what we got here. So what I say is I want to find the tension. So I need to basically, let's go to green. So I need to basically pick one or other of these. That's the one I'm going to pick. I'm going to say the sum of the forces equals MA. I'm going to say plus T added to 0. There's no other forces on this. There's the force of normal force up and the weight down, but they are perpendicular to my direction of travel, so I don't care about them. There's no frictional force. So there's only a force positive in the positive direction of T is equal to the mass, which is 7 times A, which I don't know. Oh man, if only I knew A, I could find the answer. So what I do is I change the color of my pen. And I come along and I go to purple because that's oh yeah, purple will do. And what I do is I say, there's my next bit. That's my system. And I go, the sum of the forces of the purple equals MA. And I say, plus 40. There's nothing, no external force. T's not even included in this one, is equal to the mass. And the mass is 4 plus 7, because it's both masses times A. So A is equal to 40 over 11. 40 over 11 meters per second squared. And I come back down here and I substitute in. And I say T is equal to 7 times 40 over 11, which equals 7 4s are 28, 280 over 11, which equals 280 divided by 11 equals 25.45, which is 25.45, which is newtons. So this is a bit more formulaic. It's called straightening your diagram or stretching your diagram. That curve, this guy here is a real problem because a positive going motion on the top is the same as a negative going motion down there. And they're the same. You might call that negative, might call that positive, but it's the same effect. Going to the left, going to the right is going to cause you to go down. So one feeds the other, and yet there's a sign difference. So by stretching the diagram out, I get rid of that sign difference. This 40, which you might think of as a 40 negative newtons, becomes a positive 40 newtons, and all the signs work out. And then the trick I use is I pick either mass, doesn't matter which one. And I say the sum of the forces equals MA for that mass. And I find that T will be included. In this one over here, T and the 40 would be included. So I pick the easier one. And that gives me something where I do not have A. So I need to find A without having T in the equation. So what I do is I do this whole system and I find my A. And that's the formulaic way. It's one of those few times when I really want you to learn the process because it makes life so much easier. We're basically out of time. Any questions before we go? Cool, okay. So try homeworks on both of those for next time, please.